Good morning, everybody, and thank you for joining us today for the Calculating Energy Costs webinar. My name is Lorena, and I will be co-hosting today's webinar. I will be monitoring chat and conducting polling at the end of the session, which you'll see to the right of your screen. Again, today we're going to be covering some examples of how to calculate energy costs so that you can go back to your facility and be able to calculate some of these and hopefully be able to save energy and money. We also want to thank our co-sponsors. We work really closely with the Energy Trust of Oregon and Northwest Energy Efficiency Alliance, which you see the logos in the bottom of our screen. Based on our customer feedback, they appreciate that we are aligned with them to help eliminate any confusion regarding energy efficiency and renewables for our customers. Before I introduce the presenter, I would like to show you some tools that you'll be using during the webinar. To the right of your screen, you will see several windows in different orders. So the participants window, the chat window, and at the end of the session, the polling window will appear. Under the participants window, you'll see the list of some of the people that are joining us, and there'll be some joining us throughout the sessions as they log on. Underneath the participants window, you'll also see a raise hand icon with a little hand. If throughout the session you have any immediate questions or you want to share an example, feel free to click that and then we'll unmute you, or feel free to also send any questions or suggestions or examples through the chat window, which is located normally right underneath participants, or at least on the right side of your screen. Also, on the top left corner of your screen, beneath the Quick Start tab, you'll see an arrow, a T, a line, a square, a marker. These are different tools that you'll be able to use during the session, and the instructor will let you know when to use those so that you can participate. It's supposed to be an informal session, so feel free to ask questions or type in stuff that you want the instructor to address. We do have some time dedicated at the end of the session where you'll be able to ask questions, and any questions that come through I will ask of the instructor as well. So let me go ahead and introduce John McLean. He's the Training and Education Project Manager at Portland General Electric. He has over 42 years of wide-range utility experience, which includes distribution field operations, information systems, corporate planning, budget manager, and energy efficiency programs. He also holds a bachelor's degree in business administration and an MBA in organizational effectiveness. He is also currently an adjunct faculty at Clackamas Community College and Marylhurst University. He is probably one of the most known lifelong learner who goes back to school to keep up with new technology and what's going on in the world. So feel free to ask him any questions throughout the session. So John, we'll go ahead and get you started here.
Thank you, Lorena. Well, today's agenda is all about electricity, how it's measured, calculating savings, looking at projects, evaluation, and at the end we'll talk about what's next steps, who do you call to get further advice. I'm pleased to see some familiar names out there today. I see Kurt Nichols. He's also an energy expert, so I'll rely on him to keep me straight today, and other people. I assume that you are a non-technical manager, staff, or other interested business professional. Today, this is the level of the course. You have something to do with energy-intensive systems in a non-residential place of work, campus, retail, governmental, or industrial process. You desire to learn or review fundamentals of electricity and related environmental resources such as natural gas, water, and carbon footprint. We're going to use electricity as our examples today, but many of these concepts on how to do calculations apply directly to other resources as well. We only have an hour, so we will cover just some basics about calculations, and we'll begin with calculating energy costs for equipment and systems. So we get to start right off with the basics of measuring electricity. The most common way that people use to what is electricity is to use the garden hose example out in the front yard. And the amount of force applied potential, that is the same as the garden hose example where you're looking at water pressure. Obviously, if everybody's got their sprinkler systems on in the morning and you try to take a shower, you might notice that you have lower water pressure in the shower. And certain equipment won't work like the shower head as well as if you had better water pressure. Well, in electricity, that's called the volt. So if you hear at work you've got a voltage issue, a voltage problem, could be on your side of the meter inside your building. It could be your local utility has to be involved. But volts is the pressure to move the electricity over the wires. The other example of the garden hose is if you have large sprinklers like the Rainbirds, some of the other ones that require a lot of volume of water to work properly, you may find your hose is too small. Instead of a half-inch hose, you need a 1-inch hose. If the fire truck pulls up, they have a 3 or 4-inch hose. So the volume of water moving through the hose is the same as the amp in electricity, which is the amount of electrons flowing through the wires. Obviously, the bigger the wire, the more electrons can flow, the more amps. So when you hear the term amps, quite often that is about the wire size, not the pressure of the volts. If you take volts times amps, these are two dynamics that you can control in your business or home. You have the mighty watt. Watt is the measure of power. It's a universal term. And in this case, we're going to talk about single phase. That covers most commercial and residential, and is the most common formula out there. So volts times amps gets you watts. On every label of every piece of equipment that you buy or purchase, by code, you will find a label on the box, on the equipment, on the appliance that tells you how many watts does this appliance use. Things we won't cover today, but we could cover in advanced topics. If you have three-phase power, you would have volts times amps times the square root of 3 times something called a power factor. If you have large motors in industrial process, large motors create a power factor problem. You might see that on your bill. And there is something called the ohm. Each wire has a different resistance. Each appliance has a different resistance. Those are terms you might hear. They're more advanced than today's topic, but I wanted you to know that they exist. So the next most common term that needs to be explained and understood is on your bills. About 90% of your bill is affected by an acronym called KWH. Now, normally acronyms would stand for one thing. If I said in Portland, the Timbers, they belong to MLS, that's Major League Soccer, one league. The Blazers would be NBA, National Basketball Association. But the KWH is really three things laminated together, and on this slide I've broken them apart. The first part, we go back to math and science classes in high school about, it's the metric system. So the first part is simply a K, an M, a G, and of course that list goes on. My favorite metric precursor here would be the mighty Y, which stands for yottawatt, which is 10 to the 24th, I think. So the first part of that acronym simply means how many zeros are we going to talk about. So if you have a KW, that's 1,000 watts. If you had an MW, that's 1,000,000 watts. And on down the line. The centerpiece of this acronym, KWH, can be something besides a W. It could be a V for volts, A for amps, O for ohms, and etc. So now we have a very flexible two-part acronym, a K in the front and a W, but it could be KV. You'll often hear people talk about KV as the lines outside, 12 KV, 12,000 volts. And the last part of the acronym is the one that when I talk to customers, they have the least understanding of, and that is the H, the hours. I don't know how many times we've talked to customers and asked, well, how many hours do you use this piece of equipment? How many hours is it on during a month or a year? And people go, I'm not quite sure. And this is why if you take some of our seminars on monitoring the load, it's the H that quite often is the easiest way to get energy savings is less hours, less energy. Sometimes Sometimes you'll see an A, which for budgeting people will be used about KWA, and that simply means, 8,760 hours in a year. That's 365 days times 24 hours. And we'll talk about KWA average, or MWA. Sometimes you'll see the A in the front. So those are some of the common terms, and it can be confusing until you realize that acronym doesn't stand for one thing. It's got three parts that are interchangeable. So a very flexible energy term. Here's the basic pin-it-on-the-wall chart or cheat sheet for how do you figure out how much energy a particular piece of equipment uses. This formula calculates the amount of power by any piece of equipment or process. Watts divided by 1,000 times the hours gets you kWh. And again, you can see where the label gives you watts. The divide by 1,000 is easy. When it comes to estimating the hours of use, that's the one that often is the most misestimated part of energy savings or energy costs. My example is if you had 20 light bulbs at 100 watts, that gives you 2,000 watts of energy requirement. Then you have 2,000 watts divided by 1,000. For each hour that it is used, you're using 2 kWh. Obviously, if you had an office building, you might have 200 or even 2,000 light bulbs. So this gives you an example of how that you start with how much energy does this piece of equipment use per hour. This would be how you find that out. I've had customers who actually wrote this on equipment to let people know how much energy something was using. So we get to practice our participation. As Lorena mentioned, in the upper left-hand corner, you have the choice of a symbol, the arrow, the T, the circle, but let's go use the arrow. And as you can see, I've got the arrow now, and I can move this arrow around. Every time I click, it moves the arrow. So what I'd like you to do is to solve this quick problem. How many kilowatt hours are used by a 60-watt light bulb that is on 10 hours a day for 30 days? So what you're trying to answer here is how much energy does this light bulb use in a month? And of course the formula is at the bottom. While you're doing that, I'm going to remind you of the story. The manager who took the full seminar course went back and put labels on all the equipment about how much energy was being used per hour on the equipment. Little label machine, little signs here and there. And he did track energy and did find that helping everyone understand the energy use of the different pieces of equipment really did help the behavioral side of his operating folks. And he did see a reduction in leveling off of his energy. Well, I can see all of you have done a really good job of picking 18 kilowatt hours. And sure enough, there is the answer. One of you has even discovered the highlighter, although 180 kilowatt hours is a little high in this case. So 60 divided by 1,000 times 10 times 30 is 300 hours, gives you the 18. So now what I'd like to do is I'd like to switch the light bulb to a compact fluorescent. The same amount of light now only takes 18 watts. So let's redo the calculation, and you can move your arrows to what do you think the energy use is now. And everyone's moving up. 1 kilowatt hour. Well, it's not quite that good. So the correct answer is the 18. 18 divided by 1,000 times 30 is 5.4 kilowatt hours. So this, obviously then, this also you could use to calculate these two numbers. The difference would be your energy savings. Very good. We're all engaged and we're all learning to use all kinds of different tools. So here's a little fun question I give to in the seminar. This energy formula pops up all throughout our lives, even at the movies. So if we play Jeopardy and the answer is 1,210,000,000 watts, that's the answer. What is the question? going to give you a couple of hints. There's the first hint. There's the second hint. And of course, the question by Doc Brown is, where am I going to get 1.21 gigawatts? Which is the amount, if you read the label on this DeLorean time machine, it says, oh, I require 1.21 gigawatts in order to work properly. What was interesting about this is that I looked it up, and the science is pretty close. Lightning is in this category. And back in those days, there was no power plant big enough to give him that unless he knew where lightning would strike. So there was a little bit of science in the movie Back to the Future. More interesting question, if he was an energy manager, is how many kilowatt hours does it take to charge this electric vehicle in 1 second? If we apply our formula, 1,210,000,000 watts divided by 1,000 times the number of hours, in this case 1/3600th of an hour, if you assume 1 second, you get 336 kilowatt hours is what it's going, the energy required to per use of the DeLorean time machine. So the formula works in a lot of different places. Sometimes in offices and businesses and even at home, you will hear terms tons of air conditioning or tons of refrigeration. These terms are convertible to watts. The extra number you need is what is the energy efficiency rating, that's the EER. SEER is seasonal energy efficiency rating. The point is, you need to know the efficiency in order to know how much energy do I need to get 5 tons of air conditioning into the building. In this case, you can see the higher the efficiency, the lower the watts, and that's a pretty significant number. So just saying to your purchasing manager, oh, look at the great price I got on a 5-ton unit, you would ask him, but what is the efficiency rating? If you bought the one at 10 EERs, you just locked in 20 years or 15 to 20 years at a much higher energy bill than if you had spent a little more money and gotten the one at 14 efficiency, much lower. If you divide one by the other, you can see that you would have a 40% more energy on the bill by buying the 6,000 watt air conditioner. So watch out for tons. Make sure that gets converted to watts and ask questions about the efficiency rating. Horsepower is the other term you might hear. Motors, fans, compressors, all kinds of equipment runs on motors. And again, it's not an energy efficiency rating. They actually show you the percentage efficiency rating, and it's usually on the label. 5 horsepower in this case at an 88% efficiency versus a 92% efficiency. Again, you get 5% more energy used in replacing the motor. This is another great place to talk to your purchasing managers about, well, wait a minute, it isn't just the tons, it's the efficiency. SEER rating it stands for Seasonal Energy Efficiency Rating. So let's talk about wire size. We talked about the garden hose, that if I want more amps or more volume of water, I can get a bigger hose or a bigger wire. And it turns out that line losses, remember every wire has some ohms, some resistance. You will have line loss. And it turns out that in this particular example, I have 2 60 horsepower motors. Both are the same efficiency, 48,000 watts. So they have the same efficiency rate. One motor takes 480 volts times 100 amps. Remember, volts times amps equals watts. So there's where I get my 48,000. The other motor is 240 volts, another very common voltage in businesses, but it takes 200 amps. 240 volts times 200 amps gets you these 48,000 watts. So you would think these would be equal, but they're not. And the reason is more amps or bigger amps leads to bigger wire, leads to bigger installation costs and future line losses. The example that was given to me by someone who had a relatively good-sized light manufacturing and assembly plant, a piece of equipment on the far side of the building, whereas the service was on the other side, they had a long wire run. Well, if you take that wire run and have a larger copper wire, copper is expensive, and it turned out that if they could use 480-volt equipment, they could significantly reduce the cost of that run to put in that piece of equipment. The other issue I've heard in plants and businesses is each panel, each service has an amps capacity on the panel. Again, if you get higher voltage equipment, you can get more amps through the same panel. So quite often it isn't the energy use on the bill, it's the installation and future line losses that can make a big difference. So ask these kinds of questions when people talk about making changes in your plant and facility. So I've often been asked, well, help me out, what's the right way to do this? I've given two ways that I've found successful with businesses. One is I love algebra. Just give me the formula and I can apply it. And you can see on this formula at the bottom here, watts divided by 1,000 times hours times the price is how you get to what does it cost to run a piece of equipment. Others have to break it down into steps. Step one, find the W. Either volts times amps or look at the most common way is find the label. Secondly, then get to kilowatts. In other words, divide by 1,000 to get to kW. Then figure out how many hours of use does this equipment use. And then finally, times the price. So you can either take these stepwise, step 1, 2, 3, 4, or you can use the algebra approach. But this is a little cheat sheet you can pin up and kind of remind yourself, those are the formulas I need. So let's do some math examples. These are ones that we have a specialist here in lighting, Mark Whitney. He's lighting certified. He's green building certified. And he works a lot with our customers. And this is a pretty typical example of a small one office area, 40 fixtures. Each fixture has 2 lamps and 45 watts each in them, using 90 watts total per fixture. So sometimes you'll hear in a conversation lamps, and sometimes you'll hear fixtures. In this case, fixtures is 90 watts. They're on 10 hours a day, 7 days a week. 8 cents per kilowatt hour is about the average price of electricity, and assume 30 days in a month. So if you take your calculators out and use your arrow in the upper left-hand corner again, I'd like you to see if you can do the math and come up with what does this office space use in energy bill each month for the lighting. You might need this just to evaluate a project. You could be leasing some space and want to know, well, how much of the electric bill do I allocate? Lots of good examples of why you might have to do this calculation. While you're doing that, several people have said, well, why isn't it simpler? This is always complex. And they say, oh, I hate word problems. And my answer to them is life is a word problem when you deal with energy. There are so many factors to consider. Another analogy I heard by someone who was put in charge of energy managing was that they feel like the TV show CSI Las Vegas. They're a crime scene investigator. They're an energy scene investigator, having to go, well, why is my bill so high? And start looking at equipment and writing things down and figuring things out. Both of those are legitimate approaches to energy, either life is a word problem or CSI. So we have some answers. Looks like we have a couple choices here. Let me show you the math that I did. Watts divided by 1,000 times hours times the price. In this case, 40 times 90. I had 40 fixtures at 90 watts, divided by 1,000 times 300 hours. That's 10 hours a day for 30 days, times 8 cents. I get $86.40 for example number 1. So let's take a look at another math example. And this one, I'll walk through the math, but I wanted to show that this works on any piece of equipment where you know the watts and you have some idea of hours of use. customer has a choice between two air conditioning units. They both have the same cooling capacity. In other words, they both put out the same tons of air conditioning. But their efficiencies are different. Unit 1 uses 1,200 watts. Unit 2 uses 1,000 watts. Obviously, the unit 2 is more efficient. It uses less power to produce the same amount of cold air. But it costs $100 more. So the question you're going to get if you wanted to get this project done is, when do I get my money back? The air conditioner is on, you estimate, about 6 hours a day for 4 months a year. Assume 30 days a month. The cost is about 10 cents. I love the 10-cent number because it's easy to do in my head. It's high for commercial, but it's about the same as you would see in residential right now. How many years before I get my $100 back? This is what they call the payback period, and is the most common decision-making tool that is used to screen projects. In this case, we have, what's the watts? Well, it's 1,200 watts minus the 1,000 is I'm going to save 200 watts, and I'm trying to calculate savings. So the first thing I need is the 200 watts. The next thing is, how do I get to kW, and that's divide by 1,000. The H is 4 months times 30 days times 6 hours. I have 720 H's here. And if I put all that into the formula, I get 0.2 kW times 720 times 10 cents, $14.40 a year. Now I can answer the question, when do you get your $200 back? The answer is about 6.9 years is when I would get it, assuming no change to electric rates. Now my question to you would be, what happens if the Energy Trust of Oregon or some other entity comes along and says, I will give you a $50 rebate to do this project? Well, what happens is the payback period is now different because I have the $100 minus 50. So I only have $50 out of pocket. Divide by the 1440, it's 3.5 years. So a $50 rebate cut the decision point to half with a $50 rebate. Obviously, a $60 rebate would be different every time the rebates change, which is often. The payback period would change. Likewise, it could be a month from now. The $100 is different because there's a sale on a piece of equipment. So this is a great example of how sensitive these numbers are and why you have to keep track of projects, not just, oh, this project won't go. The most common decision points I find in businesses are somewhere between 3 and 5 years. If your company has been around a long time and is pretty secure, you might see a 5-year payback rule. In that case, this project it could get done unless it had the rebate. Other businesses would be 3 years. If you're a restaurant, it might be 2 years or even less. So each business has kind of a norm that they would use for payback periods. Again, this is the most common way of using the math to screen projects. But it also says, don't give up on projects. They may turn around and become a yes with one simple change like rebates. I've been sent a question. How is a payback period in years converted to a return on investment? Well, the easiest way is to say, come and visit our next webinar, The Language of a CFO, where we'll talk about discounted methods and other methods. However, if you do take the $14.40 we talked about and divide by the 100, that would be a simple return on investment. In other words, for the next 15 or 20 years, you would collect $14.40 on your $100 investment. So return on investment, a straight ROI, is simply the invert of the payback period. Another good example of decision-making using some of the math is two compact fluorescents have the 25-watt rating and both produce the same amount of lumens. Lumens is the measure of light, not watts. So they have the same amount of light, they have the same amount of watts. One is $4, the other one is $5. But also by code, you have to see on the box, they have to put what is the estimated life of this bulb in hours. One bulb for $4 is hours. One bulb for $5 is 12,000 hours. You are asked to purchase 100 bulbs. Which CFL will you purchase? So I want you to use, again, your arrow in the upper left-hand corner or whatever symbol you would like and mark which bulb would you buy. It looks like many of you say, I get it. I'm going to buy the $5 bulb for the longer life. And others of you are saying, no, I'm going to go for the $4 bulb. It's cheaper. Both of those have aspects of being the right decision. If you were capital constrained, then you're going to go with the $4 bulb. You just don't have the capital. If you have some capital and think longer term and can act on it, the $5 bulb is a little better deal. For an extra $1, you get 4,000 extra hours of life. The next slide, I'll show you how the math would go if I were working for this particular company. I know, for example, I'm using this bulb 10 hours a day every day. It's on the whole year, so I have 3,650 hours in a year that I'm using this bulb. Well, the 8,000-hour bulb, let me use my marker over here. The 8,000-hour bulb divided by the 3,650 means that bulb is going to last 2.2 years. If I look at the other bulb for the $5 bulb and I'm still burning this bulb 3,650 hours a year, but I've got 12,000 hours, it lasts 3.3 years. So I actually, for the extra dollar, get over 1 year extra life of this bulb. Now in commercial, I had a bright young woman manager who told me, wow, that really helps, because in fluorescent technologies, you have to pay to get things recycled. You can't just throw these in the trash. Well, they just postponed their budget for paying for recycling of this stuff by 1 year. I hadn't thought of that, and that's a great non-energy benefit from getting the extra life. In summary, over the next 6.6 years, you can spend $400 3 times, or you can spend $500 2 times. So you basically are saving $200 in purchase prices over the next 6.6 years, and you're skipping one recycling, whatever that costs to recycle the bulbs. So that's a fun example about making sure your purchasing managers are on board with. It isn't just the watts; it's efficiency and it's the hours, the life of the equipment. These are all really important to calculating energy costs and making good decisions. Once you've got data, what we're finding as the world becomes more complex is you need a visual representation of what's changing and why. In this case, I took monthly bills, 4 years of information, and you have a spreadsheet with 12 months across the top and 4 years down the side, and you look at the spreadsheet and you kind of go, okay, I think I might see what's going on. But once you graph it, you can very quickly see what's going on here. You've got I put the winter in the middle, so notice that I've got December and January, the 2 biggest months for heating and cooling, or heating. I put them in the middle of the chart, so that here is the winter up here. And I've got 2 winters that are very high, and then 2 winters where my energy bills were much, much less. This was about a 40% reduction in energy. What changed and why? It turned out that this was a heat pump customer, and they replaced a standard heat pump when it broke with a high efficiency heat pump. And just going from heat pump to heat pump and the efficiency changes resulted in a dramatic change in the winter bills. Now this was pretty easy to see from a graphical point of view. It was much more difficult to explain from a spreadsheet point of view. So looking at the data and getting some kind of graphical representation is a very important part of not just calculating costs, but sharing those calculations with other people. With PGE is completed putting smart meters on all of its residential commercial customers last year, and now you have much more detailed information. In this case, this is a chart of every hour of the day for a 30-day billing period. So you have 30 days over the top of each other here. What that is giving you then is, and this is, I believe, a school. So if I can get my cursor here, this is Monday through Friday. This school is open, and by 8 o'clock, everybody's in school. And by 3 o'clock, people start leaving, and finally you're back down to midnight. This area in here is the 4 or 5 Sundays, and this area in here is the 4 or 5 Saturdays. So now you can, when I first looked at this chart, I went, wow, it's too much. But as soon as it was explained to me, it dropped into very quickly something I could use to explain things. And this is a case where you've got all this data, and you can do some calculations, but you need to be able to show the results. I like the question, what comes on at 1 a.m. every night and stays on until everybody starts coming in. For a while, this was a mystery. Back to the CSI school district person, and found that the IT department was turning on every computer in the facility and backing them up, but the software that turned on the computers automatically couldn't turn them off. So suddenly you had all these computers on with no one using them. What they did is they bought software, turned the computers off, and so now this chart here, this graph dropped down and then started going up. So they saved all this energy in here, and they could graphically show the change in the shape after they'd made the change. So if you're asking for money to make changes, graphs are a good way to show the before and after and actually see the change, rather than bringing in this monster spreadsheet and saying, look, the data changed. So we find graphics a great way to not only ask good questions, but show results of changes. What in the upper right-hand corner, when we asked why did it take so long to drop off, if everybody's left, why is all this energy out here? Well, they found out that was the janitorial services, and they came in, turned the lights on in all the classrooms and all the rooms, and when they left and completed their cleaning of a room, they would turn the lights off. This let them know what rooms they had cleaned and what rooms they had not cleaned. Well, of course, this made it easy for them to see, but it was also meaning that you were not seeing the drop on energy that you would have had. So they changed the contract and said, look, I want you to work in one part of the building at a time while the rest of the buildings are off, and only turn the lights on in the room that you're cleaning. And again, they had a dramatic change of, instead of what you see here, they got the line, pick a different, they got this to come down a lot faster, which means they saved, visually, you could see they saved, all of this went away, because they got it to go down a lot quicker. The lights were only on in the rooms that they were cleaning. So you can ask very smart questions from these charts, and you can show the results of making changes. Another dynamic of calculating energy costs, we talked about the importance of the H and the W and the K. There are probably 3 areas, I would say, that projects can be found where you can do some calculations. One is behavior. Conservation means don't waste energy. If you have a piece of equipment that's on a lot of hours and you know, in the example we just had, there's nobody in the building during those hours, that's a case of behavior. Turn the lights off. Change your behavior of what you're doing. You can also change the process. They went in and changed the janitorial process, changed the contract, and they saved. You could change operating procedures, monitor and detect unexpected conditions. And finally, the easiest one that we had examples on today were change the equipment, replace the equipment with high efficiency. So my recommended next steps, establish some kind of management feedback process to measure and monitor energy use from operations. I gave you examples where managers simply put the labels on equipment, let people know what energy uses were, put charts on the bulletin board, and they saw a behavior change. Compare energy use with benchmark. Our staff here produces benchmarks of what should a typical office building use, what should a typical restaurant use in energy, both gas and electric. Give us a call and we can share those benchmarks with you, and you can compare your building with that benchmark. If you're high, you may start asking questions about why is our building using more energy than a standard or average building. We talked about developing and maintaining a list of project ideas. And once you get a yes or a no, don't take the no's and throw them away. Every 6 months, go back to those projects, update the prices, update the incentives, update the cost of the equipment, and rerun the payback period to see if they've changed for the better. And lastly, keep learning. Stay abreast of the changing technology, energy prices, and incentives. Lorena mentioned I'm a continuous learner. Boy, in the energy business, it is changing fast and going to be many, many new offers coming out with demand response, renewables, all kinds of fun and exciting changes are coming. But you have to stay abreast. So we talked about, well, what if I need somebody to help and talk to? PGE and the Energy Trust provide free energy consultations. By phone, on site, if you're interested, there are two areas that you might give us a call. For commercial or non-residential customers, Ian Schneider-Grassman, and there's a phone number and an email. For industrial process, John Maloney with a phone number. Both of these people, there are stabs of engineers, lighting specialists that stand ready to work with our customers, help them through the processes, get them started with the trust, team up with the Office of Energy if they have tax credits. Very, very experienced people ready to help you. And with that, I think I get to turn it back to Lorena.
Thank you, John. And I do have quite a few questions that I'd like to ask of you, but before we go to that, I want to remind everybody, first of all, thank everybody for joining us, and we'll go through the questions. But to remind you that there's some upcoming webinars, as John mentioned, to learn more about the CFO's perspective and more about ROI and all those financial fun terms that we all love. It's coming up on July 26th, and then if you want to find out more on HVAC, lighting, and other technologies, we have other webinars. We also have seminars, so visit our website to find out more if you haven't registered for those. You'll also see on the right side of your screen, a polling came up. We'd really like your feedback on what you thought of our webinar, and we're always looking to improve. So any suggestions, recommendations. We also want to find out what preference of time works for you for our future webinars to be able to offer these on a time that works better for you. So please take a few minutes to fill it out as I go through the questions. We also want to remind everybody, if you did not log in with your full name, please make sure that we have your email so that you can receive the follow-up email with a recording of the session, the PDF, the materials. All right, so the first question, John, first of all, I wanted to point out, you gave some really good examples of how to calculate energy, specifically with light bulbs, but we did want to point out, as one of our participants mentioned, that does not take into account sales on bulbs or drop in light bulb prices. So it will vary depending on also what the different styles you're looking at. But John, where do you recommend that people start, for example, with a large commercial building, like an office building with 60,000 square feet, 125 full-time employees? Where would you recommend they start in figuring out how to calculate their energy costs?
A large building, lots of employees. Where do you start? I would start in that somewhere in that building there's an energy management system, an EMS, I would suspect. I would start with the benchmarking, simply understanding where is the energy use in this building and how does it compare. And that might require giving a call to the Schneider-Grassman people, or getting, if you don't already have an energy consultant or facilities manager. But there should be some way to see a pie chart of, gee, how much lighting, how much HVAC, how much office equipment, getting a handle on what the base use of energy is in the building, both gas and electric and probably water as well. That's what I hear from customers as a good starting point. From that base, then they can start asking good questions of, gee, how does this compare with other buildings? Gee, why are we high? So getting a benchmark and asking good questions. You're going to have to sometime, once you start getting answers and you have some information, share it with those 125 people. So finding a way that people care about it, having it included in staff meetings, whatever it takes. But if it's not an issue, only one person really can't affect change in a building. You can be the spark plug for changing it. You can be the energy champion, but you're really going to need everyone to be involved. Hopefully that helps.
Thanks, John. And as we saw, there's a lot of different charts that are very useful, and somebody really liked your example about the computers, leaving the computer systems backed up, and that's why they stayed up all night. You mentioned watts for different appliances and technologies. Where do you find that? And I know that some of them have nameplates, as you mentioned, but what if they don't have that? What do you recommend? Are there resources, are there services, or where would they find that?
Oh, wow. If a piece of equipment doesn't have a nameplate, then you're going to, let's assume it's a piece of HVAC equipment, an air conditioner or something like that. Quite often the vendor or an electrician or an experienced HVAC person will be able to say, oh, I remember that. That's a Benford 5000. And so find an expert that might be familiar with the equipment. I would be surprised if it didn't at least have the manufacturer name on it. So that's one way. Our people here at PGE can be called, and they can probably give you some references to some people. So if it's not got a label, then you're probably going to have to get somebody who recognizes the equipment. That's a great question to email one of the two numbers I mentioned to you, Ann Snyder-Grassman's number. And that might be another way to have send us a picture of it or something. So without a label, you're kind of stuck. If you are an electrician, you can measure the voltage with a meter. You can measure the amps it's drawing, and you could get a handle on it by measurement. But that would be the last thing I would do. I would try to find somebody who knows what the equipment is. Or, again, find an electrician that can measure the volts and amps, and given volts and amps, you can come up with watts.
Thanks, John. One of the last questions is, you shared these formulas that seem to work with any type of equipment. Where does the demand charge on the bill, where does that come into play?
The demand charge. This one is a good question. It pops up a lot. People see demand charges. They're afraid to turn on their equipment all at once. They'll get a big demand charge. Demand charge is the highest, or is the energy used in a half hour. So over 1 half hour, up pops your bill, and it says, here's the highest half hour use that you had. Now, the purpose of this is that the utility company has to build facilities that handle and provide you power at your most highest energy use, your peak. So that number gives the utility company an idea about what facility they need to build, transformer, wire size, etc. Obviously, if you're a customer that uses all your energy at once and then nothing for the rest of the week, we still have to build the facility to your peak. So that's why there's a demand charge. The demand charge for it, as part of your bill, however, is usually a very small portion of your bill. The energy experts, the engineers here, when I get trained by my people, they explain that if it's more than 10% of your bill, then you might have an issue. Otherwise, rather than an energy issue.
And so on the last question, and unless anybody else has other questions, if they want to raise their hand using the icon or submit them through chat. You talk about payback. How do you calculate payback, or how do you know, is there an industry standard on payback when you're using the formulas and for certain kinds of companies? Or what does PGE use?
PGE uses a 5-year payback as a general rule for initial screening of projects. Since we think such a long-term basis, we build power plants that last 50 years, or in one case at Oregon City, we still have our hydro facility after 120 years. So we tend to think long-term, and everything is in discounted cash flow terms, present value, net present value, internal rate of returns, those kinds of terms. So we use payback period as an initial screening. I'm told 3 years is about the most common average of businesses in general for making decisions. The most important thing I would recommend to people is find your budget manager in your facility or your company and ask them what they're using to make decisions. And if they have a 5-year, 4-year, 3-year, 2-year, quite often they will have some kind of an initial, here's the first screening level. As I mentioned, obviously restaurants who tend to be not long-term, they're going to have very short payback decision rules. So ask is my best answer. Find your budget manager.
Thanks, John. I'd like to point out that Kurt is doing some math for us, and he said that a 5-year payback is actually 20% ROI, so that's a good investment today, no matter how you look at it. He also says a 10-year payback is about 10% ROI, so still much better than a credit union pays. So again, do your math and contact John McLean if you want more details or information or have some thoughts or questions regarding how to calculate energy costs. He'll also be our instructor for the next webinar on the CFO's perspective of EE and renewables, and he has some really good stories to tell on why and how you can convince your CFO that your project is better than the others that are probably competing with you. So try to join us if you can on July 26th. We have an 8 a.m. and a noon session. And this concludes our questions, and we'll stay online a little bit longer in case anybody else has questions. So thank you again for joining us and making time for this. And if you haven't done the poll, please do participate in that, and we will end the recording. Thank you again.